Hello, I'm Logan Thompson with the Advanced Metalworks Enterprise team. Our team is sponsored by Deringer-Ney. Our team project was casting simulation of noble alloys in certain mold geometries. So we're going to talk about the background on Deringer-Ney's current casting process. We're going to talk about the casting simulations and all we did to get the values for those simulations. Then we're going to talk about our physical casting that we did to simulate to validate the simulations and all the work that went into that as well. So, for an introduction, we're using simulations to determine improvements for Deringer-Ney's ingot casting process to reduce porosity in their Paliney 1100 and platinum iridium castings. Um, so here is what the molds look like for the Paliney 1100 castings. They're the more round shape, and here's what they look like for the platinum iridium ones, aka Deringer-Ney. We used both these mold models to get molds made by the MET machine shop out of graphite for our casting. So we used InspireCast for our simulations. It's a casting simulation software by Altair that can take inputs of material data to create custom metal and mold materials, and it can simulate porosity and microporosity. So InspireCast requires a bunch of different properties. We got half of them from ThermalCalc, which is a um, way to simulate material properties and how they change based on different factors such as temperature. And we also got another good chunk of them from the physical testing we did called Gleeble testing. And then the ones with asterisks require those values as a function of temperature. We did literature search to find some of the static properties, aka the ones that were not changing as a function of temperature that are required by InspireCast, as well as to get elastic modulus equation for the data we collected there. Here's all the properties that we calculated using ThermalCalc, and here's an example of what that looks like for dynamic viscosity across the three different systems we used. So for mechanical properties at elevated temperature, because of the cost of Paliney and platinum iridium, tensile testing, which is the more traditional method, it was not a viable option because it requires much larger samples. So we used what's called Gleeble testing, which is a type of compression testing, requires a much smaller sample, and that got us elastic modulus, yield strength, and yield strength data at varying temperatures. So here is our elastic modulus values from that compared to literature values. And they weren't always perfect, but some of them got pretty close. And we were able to use that to kind of take it with a grain of salt and maybe change and experiment with the simulations and how we're getting the data for them. So for our simulation validation, we did physical castings here, but because of the cost of Paliney and platinum iridium, we couldn't actually use those. So we had to use a mock alloy, and so we chose copper nickel because of its similar properties at room temperature, and because of how the phase changes have occur within it, that also match with the noble metal systems. Yeah, so there's all that. And then for our results, we have the Gleeble testing results um, from the Gleeble testing design of experiment. So here's all our different runs, all the different test temperatures, and then the yield strengths and elastic modulus values that those provided us. And then here it is in the form of a graph with all the statistics on there, the error bars, all that. And then same thing for elastic modulus. So for the simulations, we had a design of experiment that included a high, a mid, and a low value for mold temp, pour temp, and pour time. And then we just did a bunch of different combinations of those to have 25 different runs to see which factors would actually lead to improved porosity results. So we did several different versions of this, ending with our most recent version, version 4, which has significantly increased porosity where we expect to see it compared to the previous versions. So here you can see we have some porosity starting to form in the lower section of the casting in our worst casting, while the best casting still remains porosity free. And then you see that porosity is really um, has a greater chance to form there versus our best casting, which is still porosity free. So these results are what our sponsors expect to see. So we have the casting parameters from our physical casting. So this is what we're actually at. Um, and then you can see what the physical casting looks like. This is the Cooper nickel, but it's in the molds for the platinum and the palladium, Paliney. Here's what our castings actually looked like. And so we have some next steps. We are performing density testing to check how much porosity is in those castings. And we are going to run simulations with these exact parameters we got from our castings to help validate those. We are also going to rerun some simulations with new heat transfer coefficient data we got by attaching thermocouples to our molds during our casting. We are also going to do Gleevil testing on the platinum iridium. We had some delays there because of the part breaking. That's going to happen early next week. And then our sponsors are also going to be casting with the actual alloy systems next week based on some of our parameters. And we'll have to analyze those results as well. So in conclusion, casting simulations along with CalFAD, that was thermal calc, tools can be used to reduce the formation of casting defects. And casting slower and at lower temperatures should significantly reduce the formation of porosity in the noble metal bars.